Okay, we'll just get started. And oh, by the way, like I guess maybe you guys already know this website, but it's pretty cool. So I came across this one. Is this papers with code. You put ranking for many research areas, and also apparently like have pointers to the code as well. So if you guys are kind of stuck with like research idea, maybe like, you can take a look of this one. And let's just go back like what we talked about last time, like near the end. So I double check with the paper. I'm still confused, to be honest. So he used against. So we'll talk a little bit more. So basically, both against this against model. So usually the against model, like this code, like they give a random code here. But apparently, like what I mean is like for we'll talk more about against like the generative model. But basically, like GAN's trying to train a discriminator among so a generator. At the same time, eventually we'll build a generator such that can generate signals, generate different kind of data. And in this case, like it got kind of a pre-trained model to generate image-led data for different code. From the paper, usually it gets a kind of stochastic, like, but this one it seems like it's not. So you give a different code, you give like one exact image here. So we try to train the code such as to maximize a particular class. So it's pretty simple in this case. So just you have attached to another network here doing a classification, they call it a visualized network. And then say if I want to visualize a candle, I will just try to back pop this score here. I can start with some arbitrary image and to where at the end then I want to make this score big, right? Candle score big, and then I can just send back the gradient and back all the way, not training any parameters in the network, but only training at the end of this code here. So that does appear what they do. As far as from the paper, without looking at the actual code, that's what I believe what they did. So so that's the result at that time, like for generating different kind of images. So we will still talk a little bit about like we will talk a little bit about this deep dream today, and also some style transfer, and after we will talk about some applications in like computer vision, beyond recognition. So deep dream. So you just give a guess. Like, how do you generate this? What do you think? Like, how do you have these images, like from the network? So we start with some. I give you a hint here. We start with some image, like just a drawing or painting, like normal painting, and then it put into a network. It play with it a little bit, then it create an image like this. So do you guys see this before? Yeah. Do you know how it made it? Like high level, I mean like high level idea.
It's like I'm not sure.
Yeah. You just put into an arbitrary network. Let's say you put into an Alice lab, and then they say they dream at a particular layer or level. So what they did is like, then you go to a particular. This is the exact code, but I see if I can. No, actually I don't even have illustration for the block diagram. But the idea is like you go into a particular layer and you look at the coefficients there at the layer, and typically when you back pop back the gradient, right? At this time, like what you did is like you just set the gradient as the coefficient itself. Then in effect, it's like you just amplify the effect, right? If your coefficient there is larger, you just make it like even larger, like next step. So then you emphasize everything is going to happen at that particular layer. So that's exactly what it's doing. Like it did some jittering regularization. It's just apply some jitter beforehand, and then they then they do this operation and then they just undo this jitter. But beyond that is basically just what they did. So, and it depends on the network. Then what the behavior will be like? You think of like a particular layer, you have different kind of features, right? What it is like you will, if you look at a particular, okay, take a look at the image, and for example, look at the cloud here. So if you see like what it looks like, then it will be have that particular one you activate, right? Then what you're doing is like it looks like for example here, it looks like a shape somehow to that network at that particular level. It just get get kind of amplified. So then once you get amplified, you feed it back to the original image. Something it looks like is a shape here. It will become like even more like a shape. I guess it's like a shape here or like something like that. I mean that animal. And you can see some like lots of, I don't know, cannot see very clearly. There's some building at the back. It depends on the work of network. You do this kind of dreaming, deep dream. So at the beginning, many people use the AlexNet, and the AlexNet typically they use the ImageNet data to train that. And ImageNet you have lots of dogs. So therefore, like it just have lots of dog data there. So once you look at a painting, anything slightly look like a dog will make it very much look like a dog. So therefore, they have like dogfish, I don't know, this pig snail, but there's a MO dog or all kind of like dog-like animal, or sometimes cats. And it depends on like different layers. You can also have different kind of effects also. For example, if I go to later layer, then I will see dog's faces, right? But if I go to earlier layer, there will be more low-level features. For example, I will try reinforce some kind of patterns like this. And so that's more results. There's apparently this one is a training from a different network, I believe. So you see like probably the network is trained with like lots of kind of like buildings and so on. So therefore like just create lots of buildings. So this is deep dream, and it doesn't seem to have any use there, even in terms of art. But that's quite kind of like immediately, maybe a year afterward, people have like idea that is have a lot of real application. They call it this style transfer, like neural style transfer. So it's something like you have a painting, you basically trying to combine two paintings, like you copy style from one painting, copy the content from another painting, and create a new painting. For example, like this one, this is the original. I can like copy different styles into that and create different kind of images. So for that, like of course, Adobe really love that. And I think they probably already have that in the latest version or whatever. So and this is more illustration. So this one, I guess it's hard to guess at what they did it still, because I still think like the way they managed to do it is a little bit magical. So high level wise, you can think of like you want to kind of combine the content and style. Right? You get content from one image and then you get style from another image. So high level wise, the idea is very simple. Right? So you create a final image, or like you create a cost function for a final image. The cost will be combining, okay, I want to look at the difference of or the cost for getting a content from the first image, and then that basically measure probably the difference of the content of two images, and then you have another measure trying to measure the style of one image from another image. Then you combine that as a joint cost. I'm trying to minimize that. That's the high level idea, but the content is easy to capture. Right? How content you can just go to a particular layer and say I want to fix the value of that layer, and that will be the content score. I just minimize the difference of the coefficient at that particular layer from the image I want to borrow content from. But then Oh, okay. Actually, I don't think I start a. Oh, actually, I did. And then but the style, I think I won't be able to guess how they make the style, but turns out like they some I think really smart guy, they figure out the style can be extracted this way. You can think of like if I have all the coefficient a layer, let's say a here, like for example, I take this layer here. I have a bunch of coefficient. I just vectorize that. I call it this all the coefficient here. I just call it x, let's say. And then it turns out that the style will be captured in the covariance matrix there of this x here. So what they did is like, okay, I want to fix, or like I have these two cost function as I mentioned. One is I just want to have all the coefficient try to be close to the coefficient, let's say at this particular layer. And now for the style, I would say for actually more than one layer, I will take this several layers here. I will say like the covariance matrix from this style, for these coefficients. Of course, it's just an empirical value, so I have the coefficient here, so I can compute the empirical covariance. That's basically just x transpose, something like that, or like I should subtract the mean maybe. So it will be like an approximation of the covariance matrix, right? So I want this guy, like it's image 1. So this one is close to image 2, let's say. And this will be another score. So I will just say compute the difference. So of course this will be like loss of values. This will be a matrix. I will for these several layers, actually, I will do the same thing. I'm just trying to force them to be similar. I think it's a bit hard to really very rigorously argue why this actually captured the style. But at a high level, like intuitively, you think of just a image patch, let's say, or like even just a 1D signal, something like that. What the covariance matrix saying is like, if I have something like big here, okay, if I have a fixed covariance matrix, okay, then I basically capture the shape. So for example, like if I have just a 1D signal here, so I have, this is a 1D signal here, I can impose a bias. That bias won't change the covariance there, but how this thing is going to vary will be captured by the covariance matrix somehow. So then if you think of like in terms of 2D, it can be like if you have some variation at this position, then you need to have some corresponding variation in the labeling position that would be like kind of reflected by this covariance matrix. But of course, I know it's kind of a little bit hand waving, but it just works basically. So I'm not sure that you guys will be happy with my so yeah, but yeah. So it works. I mean, it works really well. The only problem is like you see like for this original implementation, for each style, you need to do one optimization, right? So therefore, it's pretty slow. Like, you probably generate one image. It's acceptable, but it's not a kind of like not Adobe one. Like, you change one style, maybe you take several hours to do that because you redo the whole optimization problem. Oh, by the way, this I didn't mention that you can play around this. The trade-off between the style and the weight, style and the style and the feature weights as well. So if you weight more for the style, then you have something like that. If you weight more to the feature, then you have more something like this. Okay. So a improvement was quickly introduced like a year or something afterward, like around 2016. So now we trying to do this optimization and trying to create this image here such that we maximize this combined cost function, right? So now what we can do is like we can actually create just a new ledger to do that, right? So we instead, I mean, like if we create fit for a new ledger, I'm trying to train this ledger instead of trying to train this for a particular image. Then when I have a new image, I can just like put in this image here and then just go through this fit for a ledger to create this y-hat immediately. So actually, this kind of trick has been used like over and over again. Whenever you can replace a complicated operation with a feed-forward neural network and you train the network, after training, of course, training is expensive, but after you train that, it's a feed-forward neural network. It's really quick. You just, bam, 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 and then you get the result. So that's what they did there. And actually, very simple. And afterward, it's really quick, right? And then like also about the same time, like a Russian group like that one is like work from Stanford. Russian group also like create something similar, but they go even beyond that. They kind of, let's see, they introduce something called instance normalization. Actually, I won't go into detail for that, but it's like, okay, this is probably a good illustration. So actually nothing really so magical anyway. So when you have batch norm, you just remember that when we batch norm, we are normalizing for an entire batch. So for example, if my batch size is n here, I'm trying to take the average. I mean, subtract the mean for everything like in this patch here. But when I do this instant normalization, I just like I just basically the batches have size 1, so nothing. But they have something more interesting discovery there also, like in that paper, is that you vary that they do this instant normalization, and at the same time, like actually you vary that. If you remember, like when we do batch norm, we are doing basically like we normalize whatever the input coming in. You compute the mean and variance, and then you subtract mean and divide the variance to make it a unit variables, and then you convert it back again, right? You trying to train this gamma and beta such that we normalize that, and that will be, this essentially can cancel your earlier operation. But what they find out is that like actually you change this renormalization factor, it can also change the style as well. And then like immediately afterward, I guess this work is, I forgot, it's whether from Google or something, they combine this, they just use, okay, this idea from the earlier work, then they use this parameter, and instead, like for that earlier work, they just look at, okay, one style, so I can make it different in density of that style. But here, like I can combine several styles to just use a linear kind of interpolation for these style parameters. So, and if you do that, then you can not just like vary how strong is one style, but you can also like combine like different styles and also do it like in real time, because like this again is only a feed-forward network. So basically this is kind of like your lob there. You can just like tune it. Then if you want to make it like more into this style, then you just take it stronger. For example, like okay, maybe I say more clearly. So these four like have like different gammas and beta, right? So maybe I have gamma S1, beta S1 here, and then I have gamma S2 and beta S2 here, and so on and so forth. So depending on which style I want to pick, I can just take a linear combination of these parameters, and that will be able to get that particular style. So one final thing I'd like to mention is it probably is not very surprising. It's quite easy to fool the neural network, and actually, it created a whole kind of area, whole research area, and like kind of adversarial kind of network. Actually, like what do they call this? Let me actually, since I show you this page here, as I mentioned, I just have a pretty nice site that kind of adversarial, I think, like. Adversarial attack, like that's a kind of like a whole research area now. Just like you create kind of algorithm to trick the network. So for example, like here, you can just like introduce some noise to this truck here, and then like to all this image to just like create every image to that network that you think is an ostrich. And like yeah, basic all of them. So how do you think? What do you think? Like, how do you do that? So I give you this image truck. How do you make it like ostrich now? What do you think? Like how did they do that? Like how I can? So I give you this image. I give you the model, the lateral. I give you the entire model. Let's say. So Alex, that I give you the weights there. So how can you modify this image such that like I can make this image to check the lateral to think that this is say is a dog. By the way, is there anyone in? I think there's someone in Tulsa. Is someone connect? Oh, did I my? Anyway, so what do you think? Or how can I make it more like a dog? So actually, I think like what we talked about for the last time and also more or less like using a similar trick where we have this visualization. So and it, in the visualization, we're thinking, okay, what area will make it kind of activate a particular nuance, right? And that nuance can be kind of like arbitrary nuance inside the network, right? So we can also like go to trying to visualize at the end of the layer. So I mean the last layer. Let's say I have all the class score here. I have the doc score here. I can see like what kind of thing is going to activate this one, right? So I can do a back pop like for this guy. So eventually I have an image coming in. I can try, my goal is I try to make this goal as large as possible, right? And then for the west, I want to make it small. Right? I can do back pop again, but it's not like training the network, but now I'm trying to like modify the original image, right? So then basically I just like do the back pop, but I make like update on the image, but I mean deepest descent or deepest ascent, like update to maximize the score here at the image, but not all in the parameters of the network here. So it's actually exactly the same idea as where we started like today, right? So it's the same as here, right? We want to generate that, so we kind of like we just go all the way. Of course, like here like we don't. In this example, we go all the way to the code here, but in that one we go just back pop to this image here. So we'll just maximize, make the changes such that we maximize the score here for particular class. And of course, at the same time, minimize the score for the other classes. So then we can have effects like that. We just make tiny changes, but we can make it arbitrary classes if you want. So this even like generate images is unrecognizable, but you can trick the network to think that it's like 99.9 confidence that they are whatever classes you want. And this is more example. But yeah, this is of course not new because even you go to a early generation, if you're not thinking about neural network, but just think of like features, image features, and do classification. Like a very common features like in convolution, like in the last generation, is this histogram of oriented gradient. Right? This is basically a gradient of this image, and then you look at the orientation of the gradient. I mean the direction of changes, and then you can have like images have totally looks different, but they have totally same like feature representation. So it may not be too surprising. But this is a kind of a remark that like I think it's very hard to avoid as long as we have a kind of neural network is based on back problem, this kind of linear model. Like you have a class is a governed by some kind of boundary have some rigid boundary for different classes in some dimensional space, right? So as long as I have image, I know it's here. If I move more into this direction, if I know the gradient there, of course I can just make tiny changes to make it like look like some other classes. So I didn't follow like too much like what people are doing recently on this, but my impression is very hard to kind of like avoid this kind of like adversarial attack. Maybe you guys can dig into that if you're interested. Okay, so let me, I don't know, I have more slides, probably not, yeah. Not very important. So I guess like visualizing data is very interesting. Like this is what I've written like several years ago. I'm sure people did a lot now. For example, your generative network that not just generating like aspect that's also generating voices and music and so on. And as I mentioned, for you have this classifier based on this kind of linear model. This is really hard for us to avoid adversarial attack. So I guess I would just move on the next set of slides that I'd like to talk about some computation application beyond classification. So we look at example. Okay, this is several. We look at like example for like classification, and let's talk about like several like very common or like more fine-tuned like classification problem. So we can have like detection. Okay, the classification. Only classification alone can be just classify something. I classify cat here, and I only have like one salient object of interest, let's say in the scene. So, and I want to localize that. So let's say I have a bounding box for this cat. Then more complicated problem would be like I have multiple objects. Let's say I have like several dogs and I have cats here. I want to like kind of like detect all these objects of interest, and I want to localize them. And then like even further, say I may want to do a segmentation, like either this semantic segmentation will be the entire scene. I try to like for pixel wise, kind of like determine whether that pixel is like belong to a cat or belong to the tree and grass and so on. And or I can do something known as the instant segmentation. It's like object detection, but at the same time, I don't have a kind of like rectangular bounding box, but I have a very fine-tuned like mask that kind of like segment out the target there. So let's look at like one by one. Let's say look at this semantic segmentation first. So the problem is that if you think of that, it's not that difficult, because you think of like it's really a classification problem like in pixel level, right? So it's something like for each pixel, what I can do is for each pixel I look at the neighborhood, I do a classification to determine for that pixel like whether it's belong to a tree or belong to cats and so on and so forth. So we can totally build a new ledger for that, right? For example, like I can have a conv ledger like that, but since at the very end, I'm trying to classify per pixel, right? So therefore, at the very end, the size of that layer should be after in terms of like what should I say? The two-dimensional size should be the same as the image size there, right? So even though the depth there should be equal to the number of classes, then in the sense that okay, if I do it naively, I can have a conflat, same size conflat over and over again. But the problem is like this is very expensive. Like all this operation is very expensive. So typically, a better way is people do it like this. Something like a telescope structure. So you just go down and have a bottom. You just this part is like quite familiar. Right? We all quite familiar. We just do a kind of like mass pooling and so on to do downsampling every couple layers. Then we go down, down, down. But this is something new for us, where we go back upsampling. So we have this here now. We go up sampling to make it bigger, eventually go back bigger. And here we can save lots of operation by kind of make it kind of like thinner in the middle. But then the question, of course, is how do we do this upsampling? So several ways we can do it. Like we can do a Lewis label, or we can do something like this, a bag of nails. Like just instead of everything is like fill in the same thing, and we can just fill some of them. And if we do mass polling in the early layer, a better way to do is I do a mass unpolling. Actually, this is something like we also briefly mentioned when we do visualization. So we also have unpolling there, and this is actually essentially the same thing like that one. So when we do if we basically here, like if during the forward parser in the early layer, if these are the maximum value, in the later layer, in the corresponding layer, we'll only kind of like fill in the value and the corresponding coefficient of the maximum value there. So does it make sense? So this actually, honestly, you may ask like why we should do that. I think it feels like it is white, and the result is good as well. Yeah, but okay. I don't have a very good answer for that. Also, like, I'm not sure like how whether they did have comparison of this with like say this. I assume that this would be better. Like, and this is like for polling, right? If I do go down with like downsample like polling like this, then I can. Of course, like, this is like an exact opposite operation of this guy, so it kind of makes sense. So I can also downsample with using like a stripe more than one, right? For example, I can do conv or like, but like I have stripe not equal to 1, I have stripe equal to 2, then I also have a downsampling effect, right? So let's say I have a stripe equal to 2 like this. The first have this, second have this, then I have a downsample like this, right? So if I'm going backward, so I actually going backward because it's very in this case very natural. It would be like a transpose convolution. Why I say transpose is like if you think of this as a matrix multiplication. So let's say if I kind of vectorize this whole thing into a vector like that. So I have this value is something like this output here. I have like 4 values as vectors. So then this guy here is equal to this long vector multiplied by this matrix, right? So the exact opposite, if I'm going backward from now I'm here to here. If I from here to go to here, what I can do is I can do just a transpose of this guy. So I have this one multiplied by transpose of this. So this is equal to a transpose. And get back the long one here. So and in effect, what it's doing is something like this. So I have the filter, the same filter. So this is the same filter here. So if I have value here, I'll just have this value multiplied by this filter, and then plus this value multiplied by the same filter. So then for this overlapping region, we'll have like these two added together. I have some contribution from this side and also contribution from this side here. So this is kind of like you get the picture there. So and in 1D case would be something like that. So 1D case would be, so for example, if an input like this, the filter is YC here. So I have, so therefore here for the first element multiplied by this filter, I have AX, AYAC here. And then for this filter, or for this input, for this filter, I have this here. So I have something overlapping at this here. So it's very reasonable if you think of it this way. Like if you have X, let's see, you have 5 value here, for example, like And I have filter. So let's see what I have two values here as output. Maybe I call it y1, y2. So let's say, okay, it's XYZ. Let me call it ABC for the filter. So this guy, like this forward, is like this multiplied by A, this multiplied by B, this multiplied by C, and add together here, this one, right? And then like for this y2, I have this again, like A, B, C. So it's like this guy are linked to this guy with the coefficient A, right, with weight A here, right? So y1 is have contribution with x1 from x1 with a weight A. So y1 therefore is equal to A plus x1 plus B plus x2 plus C plus x3, something like that. Now, if I going back in the other direction, then it's exactly the connection between these two guys kind of symmetric. So if like this going back to this one here, so x1 is equal to y1 times A, right? And x2 is equal to y1 times B, and x3 is equal to y1 times C plus y2 times A, and so on. And this is exactly the transpose operation. Exactly equal to your output multiplied by the transpose of the weight, and get back to the input. And we have convolution operation, and the mass pooling is taken care of. Then we basically, this whole thing, we know how to do it, right? So this basically only have composed of convolution and also like, yeah. So we then with that, then we can train end to end. So when the result is quite good, and basically something like that. So okay, let's look at another problem. So let's look at like classification, but also with localization. So if I only have one object here, what should I do? Like what do you suggest? I know how to do classification. So how do I also include localization? So what's the output for localization? What do you think? If I want to localize this cat, how many bits of information or bytes of information do I need, or how many numbers of values do I need to localize this cat? Let's say just I need the bounding box here. Any guess, like any wild guess is okay. It doesn't matter. So, I hope that like this is the most useful part, right? So you just need to have some wild guess. We have a new problem now, so based on like what you know up to now, like what's the it can be wrong, right? It's okay, like and you need to come up with some idea first, right? And then you can. Is my question clear here? Like so we have previously we have this classification problem. For example, like ImageNet, we trained the whole AlexNet to classify, let's say, 1,000 classes. So any image coming in, let's say here, I have a cat here, I can classify into a cat. Basically, if you remember, okay, what's the AlexNet event? Okay, the whole thing may be complicated, but the last layer, I should have a layer with like output of 1,000 values there. So each of them will be a score, and then eventually go for a softmax, give me a probability. Then like I can see, okay, in this case, the cat class, the coefficient corresponding to cat with the highest values or closest to 1. So therefore, like I identify this as a cat. But now I want to do more. Not just I want to identify whether it's a cat or dog or something. I want to localize that object as well. So what should I do?
So your output would be a set of bounding boxes with the probability of something being inside?
Possible, but that would be like lots of like possible bounding boxes. Because
you have to.
Yeah, there are a lot. Yeah, there's a lot of possible bounding. Possible. So you have like, if you put 1,000 bounding boxes, this is not actually. Honestly, this is not a unreasonable solution. Actually, yeah. When you have one object, actually, this. Yeah, actually, what you say is what is actually good. Like even for like actually for multi-classes, but for one classes I can make it a bit simpler because I know I only have one object there, or not one classes, one object there. If I only have one object there, that bounding boxes can be represented by just four numbers, right? I can just store the two corners here. Each of them is a xy coefficient. So I have a xy coordinates. So I can store the xy coordinates for this corner and xy coordinate for this corners. So then the localization, at least for the output for the localization, can be represented using just 4 values there. And then I can, besides this classification problem, I can also include an extra head to solve a regression problem as well. I just try to kind of like for all my data, besides I want to correctly classify this cat, I also want to like find the bounding box, or like find the numbers that define the bounding box. So I can have like, if I have a network, like many layers, and something like this is the last layer here. So in the second last layer, probably is an important feature as well. I can pull this out, and I can like connect into like, let's say like 4 more values here. So here I can just simply do a regression. So like I will output 4 values here, and now my cost function, besides this classification cost, will be basically the cost entropy loss. So here I can also include a regression loss. So it's basically the area for the bounding box. Then I just can't wait to sum these two losses together. Then I can just again train the model. And potentially, if I already pre-train this whole model, then actually the only thing I need to train is just train the weights here. So that is actually all I may need to fine tune earlier a couple of layers, but that's about it. So and then that's basically what people did. So you can hear the so this is the second last layer that have basically about 4,000 coefficients. Then besides connecting to the last layer for the classification, also fully connect to another layer with just 4 values for the bounding boxes. So in that case, they try to fit the x, y, and also width and height. Yeah. So and then you have 2 losses now. You have the softmax loss, and also you have the loss from the regression. So this can be just a L2 loss. And then you add them together and then just solve that. So for problems like this, if you have one single object, for example, if I have one single object, I can also use same idea, for example, for pose estimation. Say, because if I have someone have a particular pose, the pose will be computer specified by the location of this key point there. Then I can just try to do a regression again to find all this location of the key points. So I will have another hat contain in this case maybe 8 coefficients here, and 8 variables, and I try to do a regression to fit this 8 values to this location. Actually, it should be 16 because each of them have 2 values there. So no, I guess it's pretty clear. So therefore, single object is not that difficult really. The problem is that once you get to multiple objects, then the same trick I just mentioned is not quite possible, because I don't know ahead how many hats I need. For example, if I have 2 dogs or 3 cats, so I may need if I have 2 dogs, I will need to regret 8 values, right? I mean, I have 3 cats there. I need to regret 12 values there. So I don't know ahead how many values do I need. So then what can be done is okay, that's the most naive way. That I guess it's also, if I ask you, I guess this it's good if you can come up with this idea at least, right? So the most naively, you can have just a sliding window. I can just try to slide over the entire image. I'm trying to per each sliding window, I try to recognize that object. So hopefully the sliding window is not too big and also not too small, that just big enough to kind of cover one object there. So but of course it's not very ideal apparently, because you have object smaller, you have object bigger, and also this can be quite slow. So therefore in practice not really been used. I'm not even sure anyone published anything for that. So an immediate idea will be coming from just classic computer vision. There's something they have an area in the past is trying to do this kind of vision proposal, is trying to look for an interesting object in a scene. So that is some classic approach, not neural network based. They just come up with lots of potential boxes. So these are all the candidates, and then with these candidate boxes, each of them we can try to recognize. And this is the first work around 2014. That's what people try. So then they just with the classic region proposal method, and each of them will just kind of tackle them independently. The problem again is this is really slow. So each of them is actually very expensive. So immediately, one obvious modification is that we don't really need to go for a conflict individually. This is really slow because I can have 1,000 boxes there, and many of them are overlapping each other. I'm really wasting computation to compute this convolution again and again. So what I can do is I can have the original image, compute the convolution for the whole thing, but then I just need to figure out which coefficient is correspond to this region proposal. So that's exactly this so-called fast RCNN. The original word is called RCNN. The fast RCNN will be just I will just use the same kind of classic method, determine the region proposal, but I do my conv let, just on the original image. And then I go back to each layer and try to figure out if I have this region proposal, which area is corresponding to that, what coefficient correspond to those region proposal. Then I will take those coefficient out, and then I'll just do a kind of polling, and then add some fully connected layer, and so on and so forth. And then the rest is more or less like other classification. So I want to do the classification have a head to do classification to find out what object is that, and then I have another layer to do the regression to find the location of the boxes. And then eventually again we can combine these two losses together. Then we can kind of potentially train this end to end. It's kind of complicated, but it's doable. Actually, this is the result for fast RCNN. In terms of testing, it's actually reasonably quick already. So you can see that it's about, if you exclude the computing region proposal, it's only 0.32 seconds to 1. So it's quite quick. Actually, I have the time for RCNN. I forgot what was the time for RCNN. Here. For original RCNN, even testing, it takes 47 seconds. So it's a significant improvement in terms of time. But then once you're doing so well, cutting down the time for the rest of the operations, so then it become this region proposal become expensive now. So it will be interesting to cut this down. So what can we do? So what do you think? What should we do? What can we do? Potentially, what can we do to cut down this time here? Kind of hints on that. Actually, I think I mentioned that in just today. So what can we do? This is a trick you should, by the end, when you finish this course, I think you really should remember that this is the trick that people have been using that over and over again. If some computation is expensive, just train a neural network to replace that. So I have this classic region proposal, is kind of expensive. Why don't I just train a network and try to do the job instead? So that's exactly what the same group did. The next year, they have something known as this faster RCNN. Now instead of have the classic region proposal, they create a region proposal network. Then they train on that. Now they have several heads now, getting even more complicated. But that one basically trying to spell out some of this region proposal. And then this, of course, I will have some also have some classification cost and also the regression cost regression loss. The classification loss will be like whether the region proposal is really a valid proposal or like it's not really a object. And the regression loss simply like whether it bound the object like the location like precisely. So, but again, like, this is really good to remember because like, this trick has been used by again and again. And then after they implement this trick, now they can like reduce the computation like to about 0.2 seconds for this faster RCNN. And so let's see. Let's see if I can remember this. Oh, okay. I also want to mention one of this other work here. It's called like fully connected convolutional network. So this is another trick that has been repeatedly used also in CNN. So I would just emphasize the most important part. It's like the fully convolutional part. When they say fully convolutional, what they mean is that like they remove the fully connected layer at the end. So if you see like for many conflat, for example, we mentioned even for Westlet, at the very end we have like one conv layer there. Oh, sorry, one fully connected layer here, and they have this fully convolutional network. I find it really confusing. Sometimes I will think of like whether it's a fully connected network or something like that. So, but this will be like, you simply remove the fully connected layer there at the end. So first thing is like, for fully connected layer can be expensive. So if you count the number of parameters, typically it's huge for the fully connected layer. You have lots of number of parameters and lots of computations there. So if you remove that, you can replace by, for example, average pooling. So what it means is like if you have the, or you think of like if you have the last layer. Let me give an example. For example, like if I eventually get the last layer is like that. I have like 10,000 samples here, and then like I'm trying to do a classification like into 101, and what I can do is I can have a vector 100, and then I can for each of the 100 I just connect this together. Basically, this coefficient will be average of the first 100, and then the second will be average of the second 100, and so on. So basically, in this case, there's no parameters here. Computation is much the capacity is much lower. Yeah, and there's a second advantage, like remove the fully connected layer. That may be less obvious is that like the only reason, if you think of like I need to stick my image, like for example, like for this one, I'm working with an image size of like 320 by 240, let's say, and I have a fully connected layer at the end. Basically, it's like the fully connected layer that kind of limited the size of what here can change, because like if you think of like the fully connected layer somewhere near the end, and maybe there's a layer 1,000, and before that I have like 44996 like in AlexNet. You have like many conv layer up to here, and the size of this layer, I mean the length of this layer, depend on the size of the input here, right? Remember that, for example, if I have input image is like 24 by 24, if I do a just a conflat like 3 by 3 and have a pad 1, I get back 24 by 24, let's say, right? If I keep doing convolution and so on, this output, of course, will depend on the size of my input. The size of my output will depend on the size of input. And this means that like I cannot change because it's the fully connected layer. I really cannot change the size of my input. Once I have trained the ledgers to have this particular size, if I change the size, like for example, I double this size here, my layer here will become like 80 something like that, right? And now the connection here will be totally messed up, right? Because I trained this coefficients here in the sense that it's supposed to be only like for something like so many, like only have like 4,000 inputs. Now I get like 8,000 inputs. So I this coefficient, I mean the number of coefficients just doesn't match. On the other hand, if I get away with this conv layer, the fully connected layer here, so if I change the size here, I can just like, it's still weight the same way. So I change the resolution here. Roughly speaking, like here I used to like take average of this like first 100 coefficients. Now I should take average of first 200 coefficients. But these first 200 coefficients like will still correspond to like, I mean like once my resolution get bigger or like smaller, will still correspond to more or less the same area there like in the original image. So that won't be like a big deal like you, yeah. At least you won't have like break down the ledger completely. Right? So this is a second advantage actually that this is another approach to do the detection. I want to actually this is the only thing I want to emphasize. I will go into that language itself. Maybe I just briefly mention this, then we'll end. So another lateral interest to mention is this feature pyramid network is. Oh, actually, maybe I will just leave it there to next time. I don't know. Yeah. So, yeah, I have like 2-3 minutes. Yeah, I guess I will leave it to next time maybe. Yeah. So, any questions? So I guess I can finish this next time and also like talk a little bit of our NN, but then I guess you guys were presentations, then we'll come back many weeks later and we continue to talk about our NN. We'll see. So
how are we doing the presentations next week?
Yeah.
How are we doing them? Are we using that computer?
Or I will always bring my computer, but I'm not sure like what do you have, like PowerPoint slides?
No, Google Colab.
Google Colab.
There's like probably I'll have 3 or 4 Jupyter notebooks.
If you can use your laptop, will be better. Yeah.
I can use my laptop. I just don't know how I'm going to send it to Tulsa.
Oh yeah, if you use the okay, yeah. Install Zoom as well. You can install Zoom.
I can
join
meetings. I can't create
Yeah, you can.
meetings.
Oh, you cannot create meeting.
I think you have to pay for that. It times out after 30 minutes.
Oh, okay. I think I can try to log. So you install Zoom, right? So so I guess yeah, I need to figure out my password. Every time we forget the password. Have this WeChat. You guys, I will log out for 2 weeks now. My phone like broke and then I have no way to get into my account again.
You can just send the test and get it.
I try everything. Like I have this like friends help. Like originally it worked out. It first complained that like I was not connecting for a long time, so it was suspended. Then afterwards saying that I'm installing in a new device. Then even with other people send me kind of like help or something, like it doesn't work anymore. So I don't know, like it's super. I never thought that it's like crazy, because like it's even worse than like losing password of a bank account or something.
Yeah, so I just use only one password for every account.
No, that's yeah. I don't actually. I wonder whether I created a password at all. I forgot. So I can't remember the password. I always use the phone to get in, way. But then like it sent a text message. And even worse is like I have my SIM card is from Hong Kong. I'm use that what two numbers. I can have two numbers. I register using my mainland number, and then I can receive text message, but I cannot send text message. When I send text message, it act like it's sending text message from my Hong Kong number. So and yeah, okay. I mean, I stuck like for 2 weeks now. So okay, let me.
I have
yeah.
that.
Yeah.
And I usually just hit join a meeting and then it lets me join.
Yeah.
But
Let
there's
me.
no.
Let's see. Oh, actually, what? Actually, the easiest thing is, I think this is kind of acceptable. I can set my camera here, and I just create a meeting and looking at the screen.
Okay.
That's probably will be the easiest. For that, maybe a little bit harder to see. Maybe you can make the font size a little bit bigger. Then will be. So I guess I'll just